Hello student, welcome to next lecture for matrix spaces. In last lecture, we have considered convergent sequences and their limits. Also, we have taken the theorem which is xd is a metric space and A is subset of x. Then x belongs to x is a limit point of set A. We know the definition of limit point. X is limit point of set A means for given positive radius or given r greater than 0, the intersection of open sphere with center at x of radius r minus point x with A is non-empty. That means x is limit point of set A. Then x is limit point of set A if and only there exists a sequence xn of points in A, none of which equals x. There is a sequence which does not take the value x, where limit of that sequence xn is x. As n tends to infinity, xn is equal to x. We proved this theorem. Now we prove one corollary based on the theorem. Let xd be a metric space and A is subset of x. A is closed if and only every convergent sequence of points in A has its limit in A. What is a corollary? xd is a metric space and A is subset of x. Then A is closed if and only every convergent sequence of points in A has its limit in A. If A set is closed, and x is limit point of set A, since A is closed, what is meant by closed set? A and its closure are same. A is closed means A equal to A closure. A closure is what? A union limit points of set A. As A is closed, therefore A equal to A bar means if x is limit point of set A, then x belongs to set A. As x belongs to set A, by above theorem, if x is a limit point of set A and x belongs to set A, by this theorem, there exists a sequence xn of points in A, none of which equals x such that limit n tends to infinity, xn is equal to x. By above theorem, there exists a sequence of points xn in A that converges to x, that has limit in A. Therefore, if A is closed, then we proved every convergent sequence of points in A has its limit in A. By above theorem, there exists a sequence whose limit is x and we have x belongs to set A, therefore the sequence is convergent whose limit is in A. Conversely, assume that if every convergent sequence of point in A has limit in A Again see the above theorem. If there is a convergent sequence having limit in the set A, then by above theorem x will be limit point of set A. Then by above theorem suppose that sequence is, let Xn be convergent sequence in A and limit n tends to infinity, Xn is equal to x, where x belongs to set A. Hence, what we want to prove? We want to prove set A is closed set. If we assume this statement, Xn is convergent sequence whose limit belongs to set A, then by above theorem, x is limit point of set A. Therefore, x is limit point of set A and x belongs to A. Hence, x belongs to A closure. A equal to A closure. Because of what? The sequence converges to point x belongs to A, and by above theorem, x is limit point of set A. Hence, A contains all of its limit points. Since x is arbitrary and every convergent sequence of point in A has limit in A, means each limit point of convergent sequence belongs to set A, and that point is limit point of set A, and all such points are limit points of A. That belongs to A again. Therefore, A contains all of its limit points. Hence, A is closed set. Or we can write A equal to A closure implies A is a closed set. Now we prove next theorem. Theorem is, let Xn is a sequence in a metric space Xt such that limit n tends to infinity, Xn is equal to x. Let A be the range of the sequence Xn. Then first point is, if A is finite set, then Xn equal to x for infinitely many n. B, if A is an infinite set, then x is limit point of it. In theorem, Xn is a sequence in metric space such that limit n tends to infinity, Xn is equal to x. Let A be the range of the sequence Xn. Then there are two cases. If A is finite, then Xn takes the value of x for infinitely many n. If A is an infinite set, then x is the limit point of set A. A part, given that limit n tends to infinity, Xn is equal to x. A is the range of the sequence Xn and A is range of sequence Xn. Also, in part A is finite set means we are taking limit over the finite set. Limit n tends to infinity, xn is equal to x, but a is the range of the sequence and a is finite set, means sequence has finite range. In the limiting case, xn, limit n tends to infinity, xn is equal to x, means there are infinitely many points of the sequence xn which takes the value x. As a is range of the sequence xn, which is finite set, points of the sequence or we also say range of the sequence takes value x infinite times. That is, if A is finite set, then if A is finite set, then xn is equal to x for infinitely many n. Part B, if A is infinite set, and A is the range of the sequence, we want to prove x is limit point of set A. If possible, suppose x is not a limit point of set A, as x is not limit point of set A, implies SR of x for r greater than 0, SR of x minus x intersection A is empty. The open sphere center at x radius r, whose center is deleted and its intersection with set A is empty because x is not the limit point of set A. What is the meaning of this statement? That is, their intersection contains the point x. SR of x intersection set A is equal to x. But it is given that limit n tends to infinity, call this as equation number first, xn is equal to x. The meaning of this, in the limiting case, xn converges to x, that means xn converges to point x, where x belongs to set x. Therefore, xn is convergent sequence. By definition of convergent sequence, we write this as, for given epsilon positive, there exists a natural number for which d of xn x less than epsilon for all n greater than n. This means xn belongs to S epsilon of x. Or we may consider, for given r positive, because we have considered radius r in above step, for given r greater than 0, there exists a natural number n such that d of xn x less than r, means xn is the point of the open sphere, center at x and radius is r. xn belongs to SR of x for all n greater than capital N. Hence, what this implies? This implies points of the sequence xn belongs to the open sphere whose center at x radius is equal to r for all n greater than capital N. Means if we have a sequence x1, x2, xt, xn, xn plus 1, x capital N, xn, xn plus 1 and so on. Then for all n greater than capital N, if we fix this capital N, then this is one of the point of the sequence. Then all the next points of the sequence, xn, xn plus 1, xn plus 2 and so on, that points belongs to this open sphere. And this is happening for given radius. Therefore, neither of the point of the sequence takes the value x, but for n greater than capital N, the points of the sequence belong to this open sphere. Hence, xn belongs to SR of x minus x intersection A. What we considered in equation number first, only the intersection of SR of x and A is the point x, but we are getting xn, infinitely many points xn that belongs to set A. Also, that points belongs to the intersection of SR of x minus x intersection A. A contradiction to the statement number first, a contradiction to equation 1, because in equation 1 the intersection of sphere and set A is only the singleton set x. Here we are getting infinitely many points of this intersection that does not contain x. A contradiction to equation 1, hence our assumption x is not limit point of the set A is wrong. Therefore, x is limit point of the set A. Example, show that a function d from x cross y to R defined by d of x1 y1 x2 y2 is equal to d1 of x1 x2 plus d2 of y1 y2, where x1 y1 and x2 y2 belongs to cross product of x and y is a metric on x cross y. Also, when d1 and d2 are metrics on x and y respectively, we prove this function d defines a metric on the cross product x cross y. D of x1 y1, the elements of this cross product x cross y are of the type x1 y1, x2 y2, x3 y3 and so on in the form of ordered pairs. Consider D of x1 y1, x2 y2 is equal to, what is the given definition? d1 of x1 x2 plus d2 of y1 y2, where d1x and d2y are metric spaces. First, we show non-negative axiom holds for this function d. That means we show d of x1 y1 x2 y2 greater or equal 0, as we are given this definition, and d1 d2 are metrics on the sets x and y respectively. Then d1 of x1 x2 greater or equal 0 for all x1 x2 belongs to set x and d2 of y1 y2 greater or equal to 0 for all y1 y2 belongs to set y, because of what? d1x and d2y are matrix spaces, as x d1 and y d2 are matrix spaces implies for all x1 x2 belongs to x and y1 y2 belongs to y, d1 of x1 x2 greater or equal to 0 and d2 of y1 y2 greater or equal to 0. Therefore, their addition is greater or equal to 0. Hence, d of x1 y1 x2 y2 is what? d1 of x1 x2 plus d2 of y1 y2 is greater or equal to 0, because these two terms are greater or equal to 0. Hence, d of xy greater or equal to 0, where x belongs to capital X and y belongs to capital Y. Second, d of xy is equal to 0 if and only if x is equal to y. If d of x1 y1 x2 y2 equal to 0, when this will equal to 0, if and only d1 of x1 x2 plus d2 of y1 y2 equal to 0, because this matrix is defined by this formula, d1 of x1 x2 plus d2 of y1 y2. This addition is equal to 0, but we know each of the term of this addition is greater than or equal to 0. Hence, these both the terms are 0. If and only d1 of x1 x2 equal to 0 and d2 of y1 y2 equal to 0. But d1 and d2 are matrix on the set x and y respectively. Hence, we have x1 is equal to x2 and y1 equal to y2. If and only x1 equal to x2 and y1 equal to y2, where d1 or x d1 and y d2 are matrix spaces. If x1 equal to x2 and y1 equal to y2, then the ordered pairs x1 y1 is same as x2 y2. Hence, if d of x1 y1 x2 y2 equal to 0, then x1 y1 equal to x2 y2. Therefore, d of x1 y1 x2 y2 equal to 0 if and only if x1 y1, the first element, is same as second element of the cross product x cross y. Third, symmetry property, d of x1 y1 x2 y2 is given as d1 of x1 x2 plus d2 of y1 y2. Since d1 is a metric, we can write this as d1 of x2 x1 plus d2 of y2 y1. Why? Because d1 and d2 are matrix on set x and y respectively. What this implies? This is the definition of d of x2 y2 and x1 y1. Therefore, d of x1 y1 x2 y2 is same as d of x2 y2 x1 y1. Now we prove triangle inequality, last one. It is given that d of x1 y1 x2 y2 is equal to d1 of x1 y1 plus d1 of x1 x2 plus d2 of y1 y2 Since D1 and D2 are metric spaces on X and Y respectively, then we can add a positive term on the right side. So this is less than or equal to D1 of X1, X2 plus D1 of Z1, Z2. Since D1 is metric, therefore D1 of Z1, Z2 greater than or equal to 0. We are adding the positive term towards right side, hence this equation will be in the form of inequality. The left side is what? D of x1, y1, x2, y2 is less than or equal to d1 of x1, x2 plus d1 of z1, z2 plus d2 of z1, z2 plus d2 of y1, y2. If we arrange the terms on right side, this is happening why? Because d1 of z1, z2 and d2 of z1, z2 greater than or equal to 0, where what are z1, z2? z1, z2 belongs to x and y. Hence d1 of z1, z2 greater than or equal to 0 and d2 of z1, z2 greater than or equal to 0. Only we have added this term towards right side. We arrange the right side as less than or equal to d1 of x1, x2 plus d2 of z1, z2 plus d1 of z1, z2 plus d2 of y1, y2. What is this? This represents d of x, y1, x1, z1 and x2, z2. See the definition? d of x1, y1, x2, y2 is d1 of x1, x2 plus d2 of y1, y2. We have d1 of x1, x2 and d2 of z1, z2. Hence, from this definition, we write this as d of x1, z1, x2, z2 plus this is also d of z1, y1 and z2, y2. Hence we proved d of x1, y1, x2, y2 means d of x, y less than or equal to d of x, z plus d of z, y. Hence all the four axioms of definition of metric space are satisfied by this metric D. Hence D defines a metric on the cross product x cross y. Thank you.